Good day, everybody. How are you all? Today we are going to talk about confidence interval for the population mean with unknown population standard deviation. So here I go. Confidence interval for population mean with population standard deviation unknown. So we cannot use the Z distribution anymore. We have to use the T distribution because we do not know the population standard deviation. When constructing a confidence interval where the population deviation is known, sigma is known, we use the critical value of z alpha by 2. Because the quantity x bar minus mu divided by sigma divided by square root of n has a normal distribution. Actually, what exactly is this? X bar minus mu means sample mean minus population mean in the numerator. How far that the sample mean is located away from the population mean. And then we divide by the quantity in the denominator is the standard deviation of the sampling distribution. That is standard deviation of the probability distribution of the sample means. That's what is in the denominator. Recall Z, the standard normal variable, is also defined as x minus mu divided by sigma. So as if this quantity x bar minus mu divided by sigma divided by square root of n is a Z score for the x bar, particular x bar value. Since it is a Z square, it has a normal distribution whose mean is 0, standard deviation is 1. So it's a bell-shaped distribution for when we know the population standard deviation. It is rare that we would know the value of the sigma while needing to estimate the mu. In practice, it is more common that sigma is unknown. So what they're saying that we cannot know the population standard deviation beforehand. Think of it, how absurd it is. We do not know the population mean. So how will we know the population standard deviation? That's not going to happen. When we don't know the value of sigma or population standard deviation, we replace it with sample standard deviation S. However, we cannot then use Z alpha by 2 because the quantity x bar minus mu divided by S divided by square root of n does not have a bell-shaped distribution. So we have replaced the population standard deviation in the denominator by the sample standard deviation. The distribution of this quantity is called the student's T distribution. And it's not a complete normal distribution. That is, it's not a complete bell-shaped distribution. There are actually many different students' T distribution, and they're distinguished by a quantity related to the sample size called the degrees of freedom. When using students' T distribution to construct a confidence interval for a population mean, the number of degrees of freedom is 1 less than the sample size. Point to note, each T distribution is characterized by a degree of freedom. What is a degree of freedom? Sometimes called DF, is sample size minus 1 or n minus 1. Students' T distribution are symmetric and unimodal, just like normal distribution. However, they're more spread out because S is on the average a bit smaller than sigma. Also, since S is random, replacing sigma with S increases the spread. So on the top, we have the solid curve in the top, on the top diagram, which is the Z curve, and the dashed curve is the T distribution when my degrees of freedom is 1, that my sample size is 2. The T distribution is the dashed curve, which is located below the Z curve. Notice it is spread out more in the tail area. Now we increase from 1 degree of freedom to 4 degree of freedom. That means we have increased the sample size, which was 2 previously, to 5. And notice the dash curve, which is the T curve, is approaching the Z curve. The difference between the T distribution and normal distribution is greater when the number of degrees of freedom is small. When the number of degrees of freedom is large, S tends to be close to sigma, so the T distribution is very close to normal distribution. So if you look at the lowermost diagram, you see the dashed curve is almost overlapping the solid curve, or the T distribution is approaching the Z distribution. Because the sample size is now 11, degrees of freedom is 10. So as we increase the number of degrees of freedom, S tends to be close to sigma. T distribution is also very close to the normal distribution. To find the critical value for a confidence interval, let 1 minus alpha be the confidence level is the area in the center. The critical value is then T alpha by 2 because area under the student's T distribution uh, is between minus T alpha by 2 and T alpha by 2 is 1 minus alpha. So the critical value on the left tail is minus T alpha by 2. Critical value on the right tail is T alpha by 2. Let's pick out a number. You have the table. We can do it in the calculator. Let's pick up a degrees of freedom of 3 and area in the right tail of 0.025. Area in the right tail is 0.025. Area in the left tail is also 0.025. Okay. That means area of the two tails is 0.025 times 2 is 0.05. Area in the center is 0.95. My sample size is 4, degrees of freedom is 3. If I want to find the critical value of T, so I do second verse, okay? Now with my calculator, okay, I have to find the critical value of T. Let me see how I get it. There is a way to get it in the calculator. Okay, so I go down to number 4, which is in T on TI-84, inverse of T. Okay, my area, if I am considering the T alpha by 2, area to the left of that T alpha by 2 is 0.95 for 95% confidence in the center plus 0.025 in the left tail, which is 0.975. And what is my degrees of freedom? I have said my degrees of freedom is 3 because my sample size is 4. So plug in degrees of freedom df3, then go down to PEST, hit enter, and enter twice. And the critical value of T is 3.182. Same value as in the table also. So you draw a horizontal line through degrees of freedom 3 and a vertical line in the top row at 0.025, vertical line through it, horizontal line through 3 in the first column. We intersect at 3.182, which is the critical value of T. Okay, simple random sample of size 10, that means degrees of freedom is 9, is drawn for a normal population. Find the critical value T alpha by 2 for 95% confidence interval. So second verse, then scroll down to 4. Area is 0.95 in the center plus 0.025 in the left tail, 0.975. Degrees of freedom is now 10 minus 1, 9. Go down to PEST, hit enter and enter. Critical value of T is 2.262 as highlighted in the table. If the desired number of degrees of freedom isn't listed in the table A3, then if the desired number is less than 200, use the next smaller number that is in the table. If the desired number is greater than 200, use the Z value found in the last row of table A3. Okay. So let's do one of these. Find the critical value T alpha by 2 for a 90% confidence interval with sample size 63. 90% confidence interval means area in the two tails is 1 minus 0.9, which is 0.1, then divided into two equal parts is 0.05. So area in the left tail is 0.05, area in the center is 0.9. Total area to the left of the critical value T alpha by 2 is 0.9 in the center plus 0.05 in the left tail is 0.95. So second verse 3, no, 3 will not do. So again do second verse 4 in T. Area, as I said, is 0.9 plus area in the left tail is 0.05 is 0.95. Degrees of freedom is 63 minus 1, which is 62. Paste, enter, and enter. And the critical value is 1.6698, which they got 1.671. Critical value alpha by 2 is 0.95. 0.95, area in two tails is 0.05. Area in the left tail is 0.05 divided by 2 is 0.025. So 0.95 plus area in the left tail is 0.025 is 0.975. Area to the left of T alpha by 2. So second verse 3. I always did 3. No, second verse 4. Second verse 4 empty. 0.95 in the center plus 0.025 in the left tail is 0.975. Degrees of freedom is 15 minus 1, 14. Press enter and enter. Critical value is 2.1447, which they have rounded to 2.145. The assumptions for constructing a confidence interval for a population mean are: we have a simple random sample. Sample size is large, greater than 30, or the population is approximately normal. When the sample size is small and less than equal to 30, we must check to determine whether the sample comes from a population that is approximately normal. Simple method is to draw a plot or a box plot. With TI-84, you can easily do a box plot. If there are no outliers, then we can assume the sample came from a normal distribution. Decide in each case whether the methods of this section should be used to construct a confidence interval for the population mean. Assume that sigma is unknown. Simple random sample size 8 is drawn from a distribution that is approximately normal. Since the sample of size 8 came from a bell-shaped distribution, we can use the methods discussed in this section. Okay. How about the one in the bottom corner, right corner? Non-random sample of size 212. Here the sample size is much greater than 30. So we can assume the sample came from a normal population. How about the one on the left bottom? Simple random sample of size 150 is drawn from a distribution not known to be normal. Okay, not known to be normal. So we cannot use the methods in this discussed in this section because the sample did not come from a normal population. How about the one on the bottom? Looks like there is an outlier on the right. The dot on the right is an outlier. Hence, the sample did not come from a normal distribution. So we cannot use the methods discussed in this section. So let's go directly to the one where we will use the table. T-interval command constructs confidence interval when the population standard deviation sigma is not known. This command is accessed by pressing stat and then highlighting the test menu. If the summary statistics are given, the stats option should be selected for the input option. If the raw data are given, the data option should be selected. So here are the food chemist analyzed calorie content for popular type of chocolate cookie. Following are the numbers of the calories in a sample of 8 cookies, sample size less than 30. Find the 98% confidence interval for the mean number of calories in this type of cookie. So first we will enter the data in L1, then we have to prove that the sample came from a normal population before we can apply the methods discussed here. So we have to make a box plot. So second, then plus button on top of enter button on the bottom right corner. Then number 4 is clear all list, hit enter, done. Then stat 1. In L1, we are going to enter this number 113, then 114, then 111, then 116, then 115, then 120, then 118, then 116. So 1, 2, 3, 4, 5, 6, 7, 8. Let's make a box plot of that. We don't want to see any outliers and skew. So second button, press the second button, then the y equal to key on top of it. Then number 1, plot 1 on. Second line type of chart, we should go to the fourth, 1, 2, 3, fourth kind of chart, which is a modified box plot that will show any outliers or not. Okay. After you have put the cursor on the fourth type of cursor in second line type, hit enter, it will be flashing there. Then press the zoom button, which is the top row third button, zoom, and then 9. And we see a box plot with the median or Q2 a little bit more on the left side than on the right side, but there is no outlier. And whiskers on the left and right are almost equal length. So we can conclude, since there are no outliers in this sample, the sample came from a normal distribution or a bell-shaped distribution. Then we can use the method of this chapter. So now we press Stat, highlight test on the top row, and then we scroll down to T interval. The reason we are using T interval is that because we do not know the population standard deviation. Now we have already entered the data in L1. So in the first line input, bring the cursor using the left cursor key on top of data and hit enter. Okay. So now the second line is list is L1, frequency is 1, C level should be changed to 0.98 because we want a 98% confidence interval. We go down to calculate and hit enter. And they did not calculate it, but you can say with 98% confidence interval, the actual population mean, they have the answer over here, is between 112.38 and 118.37. 38 they have rounded to 0.4 and 37 they have rounded to 0.4. But I will leave it as 112.38 is the lower boundary and 118.37 is the upper boundary of the 98% confidence interval. Okay. Sample of 123 aged people 18 to 22 reported the number of hours they spent on the internet on average week. The sample mean was 8.2 hours with a sample standard deviation 9.84 hours. Assume this is a simple random sample from the population. Construct a 95% confidence interval for mu. The population mean number of hours spent per hours per week spent on internet in that age group. First thing we have to realize that the sample is size is 123, which is much greater than 30. So we can assume this simple random sample came from a bell-shaped distribution or a normal distribution. So it meets the requirements of this chapter. Then we go stat, highlight test. We do not know the population standard deviation. We just know the sample standard deviation. So stat test, and we go down to T interval, T as in Tom, T interval, and hit enter. Now the input should be flashing on stats. So in the first line input, bring the cursor on stats and hit enter. Reason it should be flashing on stats because we know the statistics of the stats of the sample, okay, or the data from the sample. For example, sample mean X bar is 8.2. Sample standard deviation is 9.84. N sample size is 123. C level is 0.95. And then we calculate. So with 95% confidence, we can state that the actual population mean of hours spent on the internet in this age group is between 6.44 and 9.96. Okay. Now we don't have to worry about this Excel. Here is a potato chip company that wants to evaluate the accuracy of potato chip backfilling machines. Bags are labeled as containing 8 ounces of potato chips. Simple random sample of 12 bags had a mean weight of 8.12 ounces with a sample standard deviation of 0.1 ounce. Assume the weights are approximately normally distributed. That means this sample of 12 bags came from a normal population. Hence the assumptions are satisfied. So stat, test, and we go down to T interval again because we do not know the population standard deviation. Input should be flashing on stats. Sample mean is 8.12. Sample standard deviation is 0.1. Sample size is 12. C level is 0.99, and we calculate. With 99% confidence, we can state that the actual population mean will fall between 8.03 and 8.21. Okay. Company has developed a new type of light bulb and wants to estimate its mean lifetime. Simple random sample of 100 bulbs, much greater than 30. So we can assume the sample came from a normal population, had a sample mean lifetime of 750.2 hours with a sample standard deviation of 30 hours. Part A, verify the assumptions are satisfied. The assumptions are satisfied because the sample size 100 is much greater than 30, so we can assume the sample came from a normal distribution. Now we have to construct a 95% confidence interval for the population mean lifetime of all bulbs manufactured by this new process. So stat, test, and we go down to t interval since we do not know the population standard deviation. Input on stats, sample mean is 750.2. Sample standard deviation is 30. Sample size is 100. Sea level is 0.95, and we calculate. With 95% confidence, we can state that the actual population mean will fall between 744.25 and 756.15. Describe the relationship between confidence level and margin of error. So as we increase the confidence level, the margin of error increases. If you want to be more confident that our interval contains the true value, we must increase the critical value, which increases the margin of error. There is a trade-off. We would rather have a higher level of confidence than a lower level, but we would also rather have a smaller margin of error than a larger one. So here is a diagram. The one in the left is for 70% confidence level. These horizontal lines shows the left end is the lower boundary of the confidence interval of the horizontal line, any of these on the left, and the right end of the horizontal line is the upper boundary of the confidence interval. Now what is this vertical line? This vertical line is the actual value of the population mean. If you use a 70% confidence interval, notice how the width of the interval, a margin of error is small. The width is very small. But in case of 70% confidence interval, only 70 of these horizontal lines or 70 of the intervals will actually contain the population mean. This is the extreme left. Now look at the extreme right. The intervals are long. Width of the interval are much higher than the 70% confidence interval. Why? Because the confidence interval is now, confidence level has now changed from 70% to 99.7. Message, if you increase the confidence level, the width of the interval increases. You lose your accuracy. However, in this case, 99.7 of these lines, or almost all of the lines, intersect the vertical line. So the vertical line passes through almost 100% of this interval. What does it mean? It means 99.7% of these intervals will contain the population mean. The cost is we have lost our accuracy because the interval width has increased. So what is the optimum? One in the center, 95% confidence level. In this case, 95 out of the 100 intervals will actually intersect the vertical line. Or in other words, 95 intervals out of 100 intervals will contain the actual population mean. Okay. 95 intervals will cut the vertical line, intersect the vertical line, 5 intervals will not. The diagram presents 100 different 95% confidence interval. When we construct a confidence level with 95% confidence, we are going back, look at one of these confidence interval. We don't get to see any of the other confidence interval, nor do we see the vertical line that indicates where the true value of mu is. We cannot be sure whether we got the one of the confidence interval that covers mu or whether we were unlucky enough to get one of the unsuccessful ones. What we do know is that our confidence interval was constructed by a method that succeeds 95% of the time. The confidence level describes the success rate of the method used to construct a confidence interval, not the success of any particular interval. That means if we collect 100 sample data and calculate 100 confidence interval using the 95% confidence method, 95 out of the 100 intervals will contain the actual population mean, and the remaining 5 will not. Okay. So the optimum level selected, usually confidence level is 95%. Okay. So the formula is at the bottom. Is the minimum sample size necessary to construct a 95% confidence level with a given margin of error? So what is margin of error? That will be given to you is the sample mean minus the population mean. So it will be given to you, M is the margin of error. You know the confidence level that will be given to you. So you can find the critical value of Z alpha by 2. The population standard deviation is given. So N is Z alpha by 2 times sigma divided by margin of error squared. So we can reduce the margin of error by increasing the sample size. If the population standard deviation is known, the margin of error is given by, we went through this one chapter ago. Margin of error is the critical value of Z multiplied by the standard error, which is sigma divided by square root of N. From there, you do the manipulation to find the equation for N. Do not forget in N, the whole quantity inside the parenthesis is squared. Let M represent the margin of error. If the population standard deviation is known, the necessary sample size is given by this formula, which is critical value of Z multiplied by sigma divided by margin of error whole quantity squared. In case where the population standard deviation is not known, S is reasonably close to sigma for large sample size. Given a large sample n greater than 30, the necessary sample size. What is the difference between the first formula and the second formula? Assuming in the second formula that the sample size is greater than 30, sigma has been replaced by S. If the value of n is not a whole number, round it up to the nearest whole number. So here is the problem. Scientists want to estimate the mean weight of mice after they have been fed a special diet. A sample of 60 mice has been weighed, which is greater than 30. Sample standard deviation S is 3 grams. Estimate the number of mice that must be weighed for a 95% confidence interval to have a margin of error 0.5. Now for 95% confidence interval, critical value of Z or Z alpha by 2 is 1.96. So how do I do this calculation? I put a left parenthesis first. Inside the left parenthesis, I type the critical value of Z, which is 1.96. Multiply that by times the standard deviation, which is 3. And then divide it by the margin of error, which is 0.5. Put the right parenthesis. Then do not forget to square it by pressing the X square button and hit enter. The sample size is 139. We do not round it down to 138. We leave it at 139. Another problem, machine used to fill beverage cans is supposed to put exactly 12 ounces of beverage in each can, but the actual amount varies randomly from can to can in a sample of 50, much greater than 30. Standard deviation S is 0.05. Why am I telling that or emphasizing that the sample size is greater than 30? Because in that case, the sample standard deviation will be approximate representation for the population standard deviation. Okay, so simple random sample of filled cans will have their volumes measured and a 95% confidence interval for the mean filled volume will be constructed. Estimate the number of cans that must be sampled for the margin of error to be equal to 0.01. So we take the critical value of Z for 95% confidence interval, which is what? So first we put the left parenthesis. Inside the left parenthesis, first item is the critical value of Z for 95% confidence, which is 1.96, times the standard deviation, which is 0.05, divided by margin of error is 0.01. close the right parenthesis, and then square by pressing the X square button in the first column halfway down and hit enter. The actual sample size is not 96, it is 97. Okay. IQ test is designed to have scores having a standard deviation of sigma equal to 15. So here the population standard deviation is given as 15. Simple random sample of students at a large university will be given the test to in order to construct a 98% confidence interval for the mean IQ of all students at the university. How many students must be tested so that the margin of error will be equal to 3 points? The challenging thing in the problem is to calculate the critical value of Z for 98% confidence interval. I just want to remind you 98% confidence level means area in the center under the t distribution is 0.98. Total area under the t distribution is 1. So area in the two tails is 1 minus 0.98, which is 0.02. So area in each tail, because of symmetry, is 0.02 divided by 2, 0.01. Hence, the area to the left of the right critical value of t alpha by 2, is area in the center, which is 0.98, plus the area in the left tail, which is 0.01. It's not 0.02, it's 0.01. So 0.98 plus 0.01 is 0.99. So we need to find the critical value of Z. So second verse 3 this time, in now. Area to the left of the critical value of Z on the right is 0.99. How does it get 0.99? Because it's 0.98 in the center plus 0.01 in the left tail. How did you get 0.01? Because area in the two tails is 1 minus 0.98, which is 0.02. So area in each tail is 0.02 divided by 2, which is 0.01, which is added on top of 0.98, which makes it 0.99. Okay. Mean is 0. Standard deviation is 1. Do not change those because we are dealing with a standard normal curve. Paste, enter and enter. Critical value of Z is 2.326. So I place a left parenthesis, 2.326 times the standard deviation is 15 divided by margin of error 3. Right parenthesis, then square the whole quantity and hit enter, and it is 136, not 135. We do not round it down, we always round it up. Distinguish between confidence and probability. Suppose 90% confidence interval for the mean weight of a cereal box was computed to be 19.92 and 25, between 19.92 and 25.58. What does it mean? It means with 90% confidence, we can state that the actual population mean will fall between 19.92 and 20.58. It is not that there's a 90% probability that the population mean will be between these two numbers. Okay, so we are talking about a method which has a success rate of 90%. That means if we calculate 100 intervals using 100 samples, 90 of those intervals will contain the actual population mean, the remaining 10 will not. Okay, I stop here today. If you have any question, comment, please write me a note. I will respond to you as quickly as possible. If you like this video, please give me a thumbs up. I really appreciate that. That motivates me to produce more useful videos. If you like this video, share with your friends. You and your friends, please subscribe to my channel by hitting the red subscribe button at the bottom right corner and also click on the bell. The bell notifies you every time I upload a new video, which I do almost every day. Thanks for watching, and please do not forget to visit me tomorrow when I'll upload another interesting video. Thanks for watching. Take care. Have a nice day. See you next time.